When you're asked to find an approximate value of a particular solution of a differential equation using Euler's method, it's going to involve a lot of numbers, and it's going to be important for you to organize those numbers in a handy table. That way you'll be able to read it, and more importantly, your teacher will be able to read it. Don't just write down a bunch of jumbles of numbers. Make sure you organize your work, and this table is a nice way to organize it. So it's generally speaking, Euler's method will give you a starting x value, and it'll give you an ending x value, and it'll tell you the number of steps you're taking. So that should sound familiar to back when you did definite integrals, when you're finding the area under the curve. If you want to know how big each step is, well, we know the entire interval is the distance from a to b. That distance will be the difference, b minus a. And if each of the n steps are equal size, then we're just going to take b minus a, and we're going to divide that entire interval by n subintervals. So each one of our subintervals, our change in x, is going to be that same b minus a over n that we've already seen in the area problems. And then we can figure out what all of our different x values are. So we're going to start with our given x value. We're going to add delta x to that to get to our second x value. We're going to add delta x again to get to our third x value. And we're just going to keep on adding delta x until we get to our final x value. For each x value, we're going to have a corresponding y value. The corresponding y value at the beginning will be given, and that's your initial value of, in this case, 0, negative 1. The a value is going to equal 0, and the a of 0 value is, or I'm sorry, the y of 0 value is going to equal negative 1. And then we have to find the next y value. And the way we find that next y value is following the tangent line. So we have to know what direction we're going in. That's our slope. So we evaluate the slope at the point that we're currently residing at. And then using that slope, we're going to travel delta x horizontally. So if we multiply delta x times our slope, we're going to get delta y. And that should make some sense if you think about it. Rise over run. Just divide both sides of this equation by delta x, and you'll get rise over run. So that's going to be the change in y. So whatever our original y value is, we're going to add the delta y to get to our new y value. And then you should refer to the slope field in the previous video and try to make sense of where each of these parts come into play. And you just repeat this process over and over again until you get to your final answer. So if we're going to take Euler's method with one step, we generally won't see that question because that's just saying use a tangent line to approximate. And it's just one step, so we've already done that. But I'll go ahead and warm up with this. We'll go ahead and have our x value of 0 and our corresponding y value of negative 1. And then our dy dx value is going to equal, well, we're going to evaluate this at x equals 0 and y equals negative 1. So negative 1 squared is 1. 1 plus 1 is 2. So 2 in the numerator, 0 plus 2 is 2 in the denominator. Our slope is 1. If you go back to that previous video where we had the actual slope field, we remember that we started with a slope of 1. So, whoops, I shouldn't put the equals 1 there, should I? I should put the 1 here. And then the next step would be to figure out what the delta y value is. So our delta y value is whatever our previous answer is, our slope times delta x. And what is our delta x value? Well, we're starting with an x value of 0. We're going to an x value of 4. So a equals 0 and b equals 4. We're taking one step, so that's n equals 1. So delta x equals b minus a over n, or 4. So we're going to take our slope of 1 times our delta x of 4 and get a delta y of 4. And then we're going to get our new y value. New y is going to be negative 1, which was our old y, plus delta y, which is 3, and that's where we're going to end up. And since our delta x is 4, we're going to be now at the x value of 4, and our new y value is 3, and we stop. Because we have gotten to the x value that they've asked for. So y of 4 is very approximately equal to 3. To make sense of this graphically, we'll go back up to here and notice that we ended up at a y value of 3 if we followed the tangent line without changing directions once. All right, so now we're going to try the same method but with 2 steps. We're expecting the answer is going to be 2, so let's give that a try and see that we actually get that answer of 2. So again, start with an x value of 0 and a y value of -1. So since we're starting in the same place, we have the same slope, starting off at 1, but we have a new delta x value. So delta y, which is going to equal delta x times m. Well, let's figure out what our delta x value is. This time a equals 0 and b equals 4, but this time we're taking 2 steps, so n equals 2. So delta x equals 4 over 2, which is 2. So we're going to take m times delta x, which is going to be 2 each and every time. It was always 4 in this problem. This time it's going to be 2 for every single step. So 1 times 2 is 2. That's our delta y value. We started with an old y value of -1. We're going to change it by 2, so we'll add 2 to it. And now we get a new y value of -1 plus 2. Okay, that corresponds not with an x value of 4, but of an x value of 2, because we add our delta x value of 2. So that's the interim step. We haven't actually gotten to 4 yet. That's going to be our last step, but we need to repeat this process. So we have to evaluate dy dx again. This time, we're not going to evaluate dy dx at 0, -1, like we've done twice now. We're going to evaluate it at this new point, which is 2, 1. And dy dx at x equals 2, y equals 1 is going to give us, well, let's just work it out real quick. We get 2 over 4, which is 1/2. I think we already saw that on the slope field in the previous video. So our new slope is 1/2. And when we take m times 2, our slope times 2, we get a change in y of 1. So our old y value is 1. Our new y value is that old value plus the change, which is 2. And now we get y of 4 is approximately equal to 2. And again, we saw that on the slope field. We expected that answer. So all's well with the world. All right. So, of course, that's not a great approximation. We know that the answer really is less than about 1/2. So we can get more and more accurate by taking more and more steps. And each time we take those higher steps, we're going to take smaller steps. Higher number of steps, they're going to be smaller. So in orange, we'll do the 4-step Euler's method. Okay. So starting at the same place again, we have the initial value of 0, -1. And delta y this time is going to equal our slope times a new delta x value. Again, we're going to change n equal to 4, so delta x is going to equal 1. So whatever we get for dy dx, we're going to multiply that by 1. Of course, that's not going to change. So dy dx and delta y are going to be the same in this particular example. And we'll get our new y value. And again, we're starting at the same point, so we're starting with the same slope. The slope times 1 is 1, so our new y value is -1 plus 1, which is 0. Okay? Our new x value is the old x value plus, in this case, our delta x value is 1, so 1. And now we're going to get 2, and we're going to get 3, and we're going to stop at 4. So we can always fill out our x values because the delta x doesn't change. The delta y does change because it's changing based on our slope. So we'll evaluate dy dx now. We'll evaluate dy dx at this new point. We're going to evaluate that at 1, 0. And that's going to be y squared plus 1 over x plus 2. So that's going to be 1/3. We'll take our slope times delta x. We'll add that delta x or the delta y value to our old y value, and we'll get 1/3. for the new y value. Okay, and we're going to do that one more time. We're going to evaluate dy dx at our new point of 2, 1/3, and we're going to get 1/3 squared plus 1 over 2 plus 2. So this is 10/9 over 4, or 5 over 18. Gosh, I hope I'm doing this correctly. 5 over 18. Multiply that by 1, we'll get 5 over 18. We're going to add our old y value plus delta y to get our new y value. I believe that's going to be 11 over 18. So that's our new y value. These are getting kind of messy. So I might have to break down and use a calculator for this one. We'll go ahead and write this out as 3, 11 over 18. And I'll write that as 11 over 18 squared plus 1 over 3 plus 2. And I'll just pause the computer here so you don't have to listen to me. So according to my calculator, this slope is going to equal approximately 0.27, we'll say 47. Okay, so I'll put that as the slope here, 0.27-ish. Multiply that by our delta x value of 1. And then we're going to go ahead and take our old y value and we're going to add that decimal. And whatever we get, I'll go ahead and add that real quick, plus 11 over 18. And we get 0.8858. Okay. So according to Euler's method with 4 steps, we're going to get y of 4 is approximately equal to 0.8858. And you'll notice again that the answers here are supported with the slope field up here. We're getting answers that are continually getting smaller, starting at y value of 3, y value of 2, y value of 0.8858. And if we find that exact value, hopefully we'll find that it's even closer to 0.5, but a little bit lower, according to the graph. So analytically, we can actually solve this. Oops, I went too far. No, I didn't. Analytically, we can solve this by looking at dy dx equals y squared plus 1 over x plus 2. Separate the variables by dividing both sides by y squared plus 1, multiplying both sides by dx, and remembering how to anti-differentiate. So these are not inverse power rule problems. These are not even U substitution problems. This one on the left is just the arctan of y. The one on the right is just the natural log of the absolute value of x plus 2. Now, of course, we want that plus c value. Remember that our initial value is 0, -1. That's my x and my y value. So I'm going to go ahead and solve for c now. If you want to solve for y first and then solve for c, fine. It's a matter of preference. It really doesn't matter. So substituting 0 for x and -1 for y, we get this expression. Arctan of -1 is negative pi over 4. Natural log of 2 does not simplify. So we get the perhaps not very nice c value of negative pi over 4 minus the natural log of 2. So we're going to go ahead and solve for y by taking the tangent of both sides, and y equals the tangent of the natural log of the absolute value of x plus 2 plus c. Well, c is negative pi over 4 minus natural log of 2. So y of 4 is going to equal the tangent of the natural log of 6, 4 plus 2 is 6, minus all of this stuff over here. And a calculator can tell you what that is as a decimal. And according to what I typed in, I'm getting approximately 0.3239, which seems to be, according to the graph, even more